Welcome, everyone, to another deep dive. You know, globular clusters, they're always up there, just these beautiful spheres of stars. And I know you know this already, there's so much more to them than meets the eye. Like, they're seriously ancient, right?
Yeah.
Real cosmic time capsules. Like, we're talking glimpses into the early universe, clues about how galaxies formed and evolved over, what, billions of years.
Yeah.
It's incredible.
It is, and that's precisely what we're going to be exploring today.
We'll be using this really fascinating research review paper as sort of our guide. You know, we're going to delve into all the latest findings about how these stellar groupings form, evolve, and, well, eventually how they kind of meet their demise.
It's a pretty amazing journey, really, from their birth in the chaotic early universe to their eventual destruction. The story of globular clusters is one of, well, cosmic forces, internal struggles, and ultimately the lasting legacy of these incredible stellar time capsules.
I love that. Stellar time capsules. So to really kick things off, we need to start with the basics, right?
Yeah.
What exactly is a globular cluster? I mean, we all picture that classic image, right? A spherical collection of stars all bound together by gravity. But reading through this paper, I was kind of surprised to learn just how much debate there actually is about their classification. Defining them isn't as straightforward as you might think.
You're absolutely right. The definition of a globular cluster is, it's a lot more complex than it might initially appear. You see, early observations, which focus primarily on those in the Milky Way, led to some assumptions that, well, as we've learned, don't actually hold true universally.
Okay, so give us an example. Like, what did we think we knew about globular clusters that turned out to be, I guess, not always the case?
Well, for instance, there was this widespread belief that all globular clusters were metal poor,
Right.
ancient, located in galaxy halos, and chemically homogeneous. However, further research has revealed exceptions to pretty much every single one of these criteria.
The paper mentions NGC 6791. That was initially misclassified as an open cluster, right? It's like way younger and less densely packed than, your typical globular cluster. But its age, metallicity, orbit, and mass all point to it being a globular cluster. It just doesn't quite fit the mold.
Precisely. It's a great example of how our understanding is constantly evolving. And then, of course, you have the ultra-compact dwarf galaxies.
UCDs.
Yes, UCDs. They resemble globular clusters structurally, but they possess dark matter and display diverse chemical compositions. And this points to, well, a different formation pathway altogether.
So potentially they formed as the stripped-down cores of dwarf galaxies.
That's the prevailing theory, yes.
So if even defining globular clusters is a challenge, how do we even begin to understand their formation? The paper dives into this whole history of different theories, each with its own strengths and limitations. Where do we even start with that?
Well, it's a fascinating evolution of ideas, really. Early models, they assumed that globular clusters formed under, well, these unique conditions that were only present in the very early universe.
Right, because they're so old.
Exactly. Many are nearly as old as the universe itself.
Then we discovered young, massive clusters, the YMCs, forming in the present-day universe, especially during these huge galactic mergers. So did that lead to the idea that maybe all globular clusters formed during these kinds of collisions?
It did, and it's a logical conclusion, right? Mergers would have been much more common in the early universe.
But the paper also points out that the merger rate alone can't explain the sheer abundance of globular clusters, especially in lower mass galaxies or those found far from galactic centers, out in the halo regions.
That's correct. In those environments, mergers are far less frequent. So it's not the whole story.
There's also the theory that globular clusters might be leftover cores from stripped dwarf galaxies, similar to the proposed origin of UCDs, right? Does that hold water?
It's a possibility for UCDs, certainly, but the sheer number of UCDs is far too low to account for all the globular clusters we observe. And most globular clusters lack that chemical diversity we'd expect from this scenario.
So we've seen a few theories fall short. What does the current research suggest is the most likely explanation for how these things form?
Well, recent observations of high redshift galaxies, galaxies from the very early universe, have provided a new and pretty exciting perspective. Using incredibly powerful sub-millimeter telescopes, astronomers have discovered that the interstellar medium, the ISM, in these early galaxies was unbelievably dense and turbulent. And what's really interesting is that these conditions mirror those we find in present-day galaxy mergers, where we see those YMCs forming.
So are you saying the conditions needed for globular cluster formation weren't unique to the early universe after all?
Exactly. The early universe was just a more extreme environment overall. High pressures and turbulence were basically the norm. This means the conditions needed to form these massive, dense star clusters were widespread, and those that managed to survive long enough became the globular clusters we see today.
I see. So globular clusters aren't just like products of these special events. They're a natural outcome of regular star formation, just under much more intense conditions. But that brings up another question, right? We know all stars form in molecular clouds, these massive clouds of gas and dust. Why don't most stars end up in clusters?
That's a great question. And to answer it, we need to understand what actually determines whether a group of stars will remain bound together as a cluster or not. And the key factor here is something called stellar feedback.
Oh, what?
It's basically the energy input from young stars back into their environment.
So the stars themselves can actually disrupt the very cloud they formed from.
Exactly. Massive young stars, in particular, they pump out tremendous amounts of energy. This energy can disrupt their parent molecular cloud and actually hinder further star formation.
It's like a battle between gravity trying to pull everything together and the stars pushing everything apart.
Precisely. It's a tug of war. And the winner is determined by the star formation efficiency, or SFE.
SFE. Okay, remind me what that is again.
It's the percentage of gas in a cloud that actually gets converted into stars. Early theoretical models, working with, well, fairly idealized conditions, proposed that an SFE of over 30% was needed for a cluster to become gravitationally bound.
So anything less than that and the feedback wins, the cloud disperses before a stable cluster can form.
Exactly. But those early models, while they were often oversimplified, they didn't account for the true complexity of the interstellar medium.
So how has our understanding of SFE and cluster formation changed with, more sophisticated research and simulations?
Well, now we can factor in that chaotic, turbulent nature of the ISM. Modern simulations can paint a much more realistic picture. And one key insight is this model of hierarchical cluster assembly within giant molecular clouds, the GMCs.
A hierarchical cluster assembly, so not all stars form at once.
Right. Imagine denser regions within a GMC collapsing first, forming these smaller gravitationally bound clusters. Then, as the GMC evolves, these clusters actually merge and grow hierarchically.
The paper has this really cool visualization of this process. You see these smaller clusters kind of emerging from the densest parts of a GMC, and as the surrounding gas is blown away, only these tightly bound clusters remain. It's like a sculptor chipping away at marble, revealing the form within.
I love that analogy. It perfectly captures the essence of this process. And this brings us to the concept of cluster formation efficiency, or CFE.
CFE.
It essentially measures what fraction of star formation in a given environment results in bound clusters. It integrates bound cluster formation over the entire range of gas densities we find in the ISM.
And this is where those high-pressure environments in the early universe become critical again, right?
Absolutely. High gas pressure leads to a much wider spread of gas densities within the ISM. Think of it like shaking a snow globe. The snowflakes disperse more evenly. This broader distribution means a larger fraction of the gas sits at those high densities where the CFE is highest, favoring bound cluster formation.
So a really dense YMC, for example, would have a higher CFE compared to a more loosely bound OB association.
Exactly. And then there's the initial cluster mass function, the ICMF.
Okay, what's that?
It describes the distribution of cluster masses at their birth. And studies show that the upper mass limit of this ICMF is directly related to the star formation rate surface density.
Meaning higher star formation rates, like those found in the early universe, naturally lead to the formation of more massive clusters. Makes sense.
Yeah.
But it seems high pressure and high star formation rates aren't the only things influencing cluster formation. The research also highlights the role of galactic rotation, particularly in limiting the formation of the most massive clusters.
That's right. High rotation rates, which we often see in galactic centers, can actually suppress the formation of the largest clusters. Even in regions with high pressure, those rotational forces prevent gas from accumulating into the extremely dense concentrations needed to form the absolute most massive clusters.
So rotation acts as kind of a counterbalance to pressure, preventing things from getting too extreme. But doesn't that contradict the idea that most globular clusters formed in the early universe when galaxies were rotating faster?
It's a good point, but the rotation-limited model predicts that the most massive clusters should form in high-pressure environments, but away from the centers of galaxies where rotation is strongest. And this aligns with what we observe. For example, in the Milky Way's central molecular zone, where rotation dominates, the most massive clusters are only about 10,000 solar masses. But in high-pressure environments, like those found in those high redshift galaxies, the upper mass limit can reach millions, even hundreds of millions of solar masses.
So it's a complex interplay of factors. We've got pressure, star formation rate, rotation, all working together to shape the formation of globular clusters.
Exactly. And that's just the beginning. The formation of a globular cluster is just the first chapter in a much longer story.
Right. What happens next? How do these clusters evolve and, well, how do they ultimately face their destruction?
Ah, the inevitable destruction. That's a story for our next installment. It's a tale of cosmic forces, internal struggles, and the lasting legacy of these stellar time capsules.
I can't wait to dive into that. Join us next time as we explore the perilous journey of globular clusters through the vastness of space and time.
Welcome back to our exploration of globular clusters.
Last time, we really dug into those fascinating processes that, lead to the formation of these incredible stellar groupings. We saw how that high-pressure, turbulent environment of the early universe, it really provided like the ideal conditions for forming those massive, dense clusters that would eventually become the globular clusters we see today. And we talked about that delicate balance, right, between gravity and stellar feedback and how that determines whether a cluster can even survive those chaotic early stages.
Right, right. It's amazing, isn't it?
But of course, the journey of a globular cluster doesn't just end with its formation, right?
Oh, absolutely not. That's just the beginning, really. It's the start of a much longer and honestly much more perilous journey, a story of survival against these relentless forces that are constantly at work trying to tear these clusters apart.
So let's talk about destruction. What are the main threats that globular clusters face during their, incredibly long lifetimes?
Well, globular clusters are constantly bombarded by both external and internal forces that can lead to their demise. Externally, the gravitational influence of their host galaxies can be a major disruptor. As globular clusters orbit within a galaxy, they experience these things called tidal shocks.
Tidal shocks. Okay, break that down for me. What's a tidal shock and why is it so disruptive to a globular cluster?
Sure. Imagine a globular cluster passing through, say, the dense spiral arm of a galaxy. Or maybe it encounters a giant molecular cloud. These encounters deliver these powerful gravitational jolts, and it increases the cluster's overall energy. And if that injected energy is high enough, well, it can overcome the gravitational bonds that are holding the cluster together, and it can actually cause it to break apart.
Wow. It's like a cosmic earthquake, shaking the cluster's foundations.
I like that. That's a great way to put it. And the research actually points out this rather sobering fact. Even the most massive globular cluster progenitors, those that are destined to become the largest, most enduring clusters, they couldn't survive more than 1 billion years in their natal environments without succumbing to these tidal shocks.
1 billion years. That's incredibly short on, cosmic timescales.
Yes.
So for a globular cluster to actually survive to old age, it needs to escape that turbulent, high-pressure environment where it formed. It's got to get out of there.
You got it. Migration is absolutely key to globular cluster survival. Those clusters that manage to move away from their birthplaces, into these quieter regions of the galaxy, those are the ones that have a much better chance of reaching old age.
The paper has a formula, equation 3, for actually calculating the mass loss rate due to tidal shocks. And it looks pretty complex. There are a lot of factors involved there.
Yeah, it's not a simple equation. It takes into account the mass of the cluster, the density of the surrounding environment, and the frequency and strength of those tidal encounters. And simulations using this formula show just how dramatic these tidal shock events can be. You can actually see clusters being, literally torn apart over relatively short timescales.
It's almost violent when you think about it.
It is. It really is.
But tidal shocks aren't the only external threat, right? There's also dynamical friction.
Oh, right. Dynamical friction, that's another one. It affects globular clusters as they move through the galaxy. It's basically a drag force that arises from those gravitational interactions between the globular cluster and the surrounding, well, everything, really. The stars, the dark matter, all that stuff in the galaxy. As the globular cluster, plows through all that material, it creates this gravitational wake behind it. And this wake, it actually exerts a pull on the cluster, slowing it down, causing it to lose energy.
So it's like the cluster's dragging a weight behind it, constantly losing momentum.
Exactly, a perfect analogy. And of course, this loss of energy has consequences. Dynamical friction causes globular clusters to spiral inward toward the center of the galaxy, and, well, that's often where they meet their ultimate demise, either ripped apart by the intense gravitational forces near the center or swallowed whole by the galaxy's central supermassive black hole.
That's kind of a grim fate.
Yeah, it's not a happy ending for sure, but it's a testament to the power of gravity and those relentless forces that shape the evolution of galaxies. But it's important to remember that dynamical friction is a very gradual process, especially compared to the sudden violence of those tidal shocks.
Okay, so we've covered the external threats, but what about internal threats? Are there processes within the globular cluster itself that can contribute to its destruction?
Absolutely. The primary internal process is something called tidal evaporation. It's basically the slow but steady leakage of stars from the cluster's outskirts.
So instead of being ripped apart by external forces, it kind of dissolves from within.
Exactly. Over time, you get these close encounters between stars, especially those involving, say, binary systems or black holes. These encounters can give some stars enough energy to actually escape the cluster's gravitational pull. And this leads to a gradual decrease in the cluster's mass and, over time, a loosening of its structure.
And the paper gives another formula for this. Equation 5, right, showing how the rate of evaporation depends on the cluster's mass and the strength of its gravitational field.
Right. And it's important to note that while evaporation is a significant factor, it's primarily effective in lower mass clusters. More massive clusters, like your typical globular clusters, they're much better able to retain their stars over long periods because they have those stronger gravitational fields.
So it seems like a globular cluster's ultimate fate really comes down to a combination of factors. Its mass, its location within the galaxy, and of course those specific environmental conditions it encounters.
You got it. It's a complex interplay of these factors that determines whether a globular cluster will survive for billions of years, gradually fading through evaporation, or be torn apart by those tidal forces in a much, much shorter time span.
It's almost tragic. But even in their destruction, globular clusters offer us these valuable insights, don't they? They become tools for galactic archaeology.
Absolutely. Globular clusters are like cosmic fossils. They've preserved information about the conditions and events that shape their formation. By studying their distribution, their ages, metallicities, and kinematics, we can glean clues about the mergers, accretion events, and really the entire star formation histories of their host galaxies.
It's incredible to think that these ancient star clusters, even in their demise, can illuminate that grand narrative of galactic evolution. So how exactly do we use them as tools for galactic archaeology? What specific information can we extract from these stellar fossils? Welcome back to our deep dive into the world of globular clusters. Last time, we explored their formation in the chaotic early universe. We delved into the forces that can tear them apart. And now we're going to uncover how these clusters serve as these valuable tools for galactic archaeology.
Exactly. They're not just beautiful objects to observe, they're remnants of the building blocks that formed galaxies like our own Milky Way. They carry within them the stories of, well, galactic mergers, accretion events, the evolution of the universe itself. It's really quite remarkable.
So we're essentially using globular clusters to look back in time to uncover the secrets of galactic assembly. But how exactly do we do that? What kind of information can we extract from these stellar fossils?
Well, one of the key pieces of information is the age of globular clusters. As we discussed, globular clusters are incredibly old, some nearly as old as the universe itself. But crucially, not all globular clusters are the same age. By accurately measuring the ages of globular clusters within a galaxy, we can begin to understand the timeline of that galaxy's formation.
So older globular clusters would point to earlier periods of star formation, perhaps in the progenitor galaxies that eventually merged to form the larger galaxy we see today.
Precisely, and this is where the pioneering work of Searle and Zinn back in 1978 comes in. They studied the ages and metallicities of globular clusters in the Milky Way and found a distinct pattern. Globular clusters in the outer halo of our galaxy showed a wider range of ages compared to those in the inner regions. This led them to propose that the outer halo globular clusters originated from smaller galaxies that were accreted by the Milky Way over time.
That's fascinating. So the distribution of globular cluster ages can reveal the hierarchical nature of galaxy assembly, how smaller galaxies are gobbled up by larger ones over billions of years. It seems like metallicity also plays a role in this analysis. Could you expand on that a bit?
Of course, metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. Globular clusters, particularly those that formed early in the universe, tend to have lower metallicities than stars that formed later. This is because the early universe was primarily composed of hydrogen and helium, with heavier elements being produced gradually through stellar nucleosynthesis.
So a globular cluster with a very low metallicity would suggest it formed very early in the universe, perhaps even before the Milky Way itself fully formed.
Exactly. And this is further supported by the discovery of the Sagittarius Dwarf Galaxy, a small galaxy currently being torn apart and absorbed by the Milky Way. Many of the globular clusters associated with Sagittarius have lower metallicities at a given age compared to those that formed within the Milky Way itself.
So by combining age and metallicity, we can start to identify groups of globular clusters that likely originated from the same progenitor galaxy. It's like using fingerprints to track down the culprits in a galactic crime scene.
A very apt analogy. And in recent years, our ability to conduct this kind of galactic detective work has been revolutionized by the Gaia mission. Gaia has provided incredibly precise measurements of the positions, motions, and distances of stars in the Milky Way, including those in globular clusters.
So not only do we have age and metallicity, but we now have detailed information about the orbits of globular clusters within the galaxy. We're really getting a complete picture.
Exactly. This kinematic data allows us to identify groups of globular clusters that share similar orbits, further strengthening the case for their common origin. We can now paint a much more detailed picture of how the Milky Way assembled over time, piecing together the contributions from various progenitor galaxies.
This really highlights the power of combining different types of data ages, metallicities, and kinematics to unlock the secrets hidden within globular clusters. It's like having multiple witnesses to a cosmic event, each providing a unique perspective.
Indeed. And as our understanding of globular cluster formation and evolution continues to improve, so too will our ability to use them as tools for galactic archaeology. We're on the cusp of a new era in our understanding of the Milky Way's history, and globular clusters are leading the way.
That's incredibly exciting. The paper also mentions that observations with the James Webb Space Telescope, or JWST, are allowing us to observe protoglobular clusters, the progenitors of globular clusters forming in distant galaxies.
Yes, and it's a truly remarkable development. By observing these protoglobular clusters, we can test our theories of globular cluster formation in the early universe. We can see firsthand how these clusters form, evolve, and potentially be destroyed.
So it's like watching a time-lapse movie of globular cluster formation, providing a direct link between the conditions in the early universe and the globular clusters we see today. What a fantastic opportunity.
It is. And the JWST observations are confirming that the conditions for globular cluster formation were indeed more common in the early universe. We're also gaining insights into the early stages of cluster evolution, including the role of stellar feedback and the buildup of multiple stellar populations within globular clusters.
Multiple stellar populations. Can you explain what that means?
Sure, it was once thought that all the stars within a globular cluster formed at roughly the same time. However, observations have shown that many globular clusters contain stars with a range of ages and chemical compositions. This suggests that star formation within globular clusters wasn't a single event, but occurred in multiple bursts or generations.
Wow, so these already incredibly complex and fascinating objects are even more intricate than we initially thought. We have these ancient stellar groupings that formed in the early universe, witness the assembly of galaxies, and potentially harbor multiple generations of stars. It's mind-boggling to think about the vastness of time and the intricate processes that have shaped these objects.
It is. And as we conclude our deep dive, I want to leave you with a thought to ponder. We've learned how globular clusters form, how they're destroyed, and how they can be used to trace the history of galaxies. But one question remains. Which of the protoglobular clusters we observe today, those nascent clusters in distant galaxies, will survive the perils of the universe to become the globular clusters of the future?
It's a question that challenges us to consider the vastness of time and the intricate dance of cosmic forces. It reminds us that the universe is constantly evolving, with new structures forming and old ones fading away. But through it all, the story of globular clusters continues, a tale written in starlight spanning billions of years. Thank you for joining us on this journey of exploration and discovery. We hope you've gained a deeper appreciation for these remarkable stellar groupings and the secrets they hold. Until next time, keep looking up at the wonders of the cosmos.